All right, hello everybody. This is Ms. Schramm, and today we are talking about protons and valence electrons. So at the end of this video, students will be able to identify that protons determine an element's identity and valence electrons determine its chemical properties. So first I want to go over some atomic vocabulary. So within an atom we have electrons, protons, and neutrons. We're going to cover those definitions quickly. So neutrons are subatomic particles that have no electrical charge and it is present in all atomic nuclei except those of hydrogen. Protons are the subatomic particles that have a positive charge of electricity. Electrons are the subatomic particles that have a negative charge and travels around the nucleus of the atom. So before we get started, I want to go over the periodic table and kind of explain how the protons determine the element's identity. So if you look at the first box on the periodic table, you will see a 1, which is the atomic number, and H, which stands for hydrogen. So hydrogen is an element that has 1 proton. If you go across, you will see a 2 and an HE. That HE stands for helium. The atomic number is 2 because there are 2 protons. If you go down to the second row back on the left, you will see an Li with a 3. Lithium is atomic number 3, and it has 3 protons. As you continue across the periodic table from left to right, you will see those numbers increasing. As you add protons, the element changes. So it goes all the way from 1, and then you will see it to 118 of our known elements. All right, so let's get into atomic structure. So the neutrons and protons are held together in the nucleus by a strong force. The electrons are held around the atom by electrical attraction between the negative and positive charges. So first we're going to look at hydrogen. And hydrogen does not have a neutron. So the red circle represents the single proton, and the yellow circle represents the single electron. If we look at helium, the atomic number is 2. So there are 2 protons in the nucleus, 2 neutrons in the nucleus, and 2 electrons traveling around the nucleus. Next, I have this diagram. This is showing the different energy levels. So at the middle, we have the nucleus. For now, for our purposes, I just left it as one red circle. So that represents the protons, the neutrons, all of that in there. Because what we're focusing is on the energy shells or the energy levels. So the first circle around the nucleus is the first energy level. Now that energy level can hold 2 electrons. Then as we move outward, the second energy level can hold 8 electrons. Again, the third energy level, we have 8 electrons. So the way this works is just like you're going to the store. So pretend the nucleus is Target, and you want to park as close to the store as possible. Just like that, the electrons want to be as near to the nucleus as possible. So as we fill in our charts and our diagrams of different elements and their atoms, we are going to fill in the closest spots first. So we go to the first energy level, then the second, and the third. So let's try that for a second. Okay, so hydrogen. Hydrogen, like I said, is number 1 on the periodic table. So I'm going to write next to that nucleus 1p+. That stands for 1 proton. P+ stands for proton. Now you'll see I have 1 energy level. We are going to assume for our purposes that this hydrogen atom is balanced. So that means it will have 1 electron for its 1 proton. But there are 2 spots available. That's okay. I will fill in 1, changing it to yellow. And this kind of white circle just represents an extra space. So it could attain another electron, but for our purposes, like I said, it is balanced, so it has 1 proton, 1 electron. All right, our next example is going to be lithium. So lithium is number 3 on the periodic table, and you'll see at the center of the nucleus I've written 3p+. That means it'll have 3 protons. Now, we need to fill in 3 electrons. So the first energy level has 2 spots. So we fill in those 2 spots, and then in the next energy level, we will fill in 1 because 2 plus 1. So you'll see 3 electrons are filled in. So the rest of those spots on the outer shell are open. Next we have sodium. Now sodium is number 11 on the periodic table. So I've written 11p+. That means we are going to fill in 11 spots for the electrons. So the first shell has 2 spots. The second has 8. So that's going to fill up the first energy level, the second energy level, and then we're going to have 1 left over in the third. So that is what that would look like. The first 2 energy levels are full, and there's 1 remaining on the outside. Now, when I put all these elements and their atoms next to each other, you may notice a pattern. So the pattern is that each one of them has an outer shell that just has 1 electron filled in. The rest are empty. So that outer shell is, well, all the electrons on that outer shell are the valence electrons. That is called the valence shell, the valence electrons. So those are kind of the outermost shell. Okay, so far so good. So valence electrons are the electrons on the outermost shell or energy level. Okay, so going back to our periodic table, I've taken out the names and all the numbers just to kind of point out where you can locate elements with certain number of valence electrons. So if you look at the first column with the number 1, all of the elements in that column have 1 valence electron. Just like the ones we just talked about, they all had 1 valence electron. In the second row, there will be 2 valence electrons. And we're going to skip the middle for our purposes today and go right to the other side. And we have 3, 4, 5, all the way to 8. And remember, 8, those have an outer shell or valence shell that are full. So those valence electrons fill up the entire outer shell. So something we need to know about valence electrons, because that was half of our focus was the protons determining the element's identity, while valence electrons are important indicators of an element's chemical properties. They are the ones gained, lost, or shared during a chemical reaction. So in general, atoms are most stable and least reactive when their outermost shell is full. So that would mean on the left, the elements on the periodic table are least stable and more reactive, right? Because they do not have a full shell. And then as you continue across, the atoms that are most stable are the ones that are full. So let's go over an H2O molecule, water molecule, and see what it would look like and see how they react. So H2O stands for 2 hydrogens and 1 oxygen. So I've drawn 2 hydrogen atoms. They each have 1 valence electron. So it's just the same diagram as before, except for I've removed the empty spaces. So then we're going to see oxygen. Now oxygen, let's see how many electrons it has. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has 8 electrons total. It is number 8 on the periodic table, and we know that it would be most stable if that outer shell is full. Oxygen's outer shell only has 6 valence electrons. Luckily for oxygen, hydrogen each has 1 valence electron. So if we add 2 valence electrons from hydrogen to 6 valence electrons from oxygen, that would fill that outer shell. 2 plus 6 is 8. That would complete our outer shell. So let's see what that looks like. they can bond together and share those valence electrons. So hydrogen and oxygen easily combine or interact to create water. So here's a water molecule. Now they're stable together because that valence electron shell on all three of those atoms are full. All right, so my challenge to you is on a piece of paper, draw the atomic structures for the following elements and determine the number of valence electrons. So we have neon, sulfur, fluorine, and aluminum. All right, have fun. Hope to see you next time.